Okay, so this was just a quick review for all of you. Our goal was maximize cash flow, and you do that by reducing the time that jobs spend in the queue. Quality is number one. You take responsibility for your work. You can't have a separate department or person coming and tell you, oh, this was right or wrong. Next slide, please. Next. Okay, so this was your layout. I'm the so-called material handler. This is the shipping. We measure performance that way. Next slide, please. Okay, this is your route sheet again. So key thing to understand, and again, if you look at your handout now, you'll see a complete list of products listed. If you go to page 3, sure. If you go to page 3, anybody need the handout for today? Anybody? Okay, just pass it around. Just pass it around. Okay. So what we have today, go ahead, yeah, just go ahead, collect your handout. That shouldn't be a problem. So what you will see, this is the classic job shop situation. Different part routings, different work content. Next slide, please. This is how each operator has to do their work. Please be careful. Know the machine you are. Check when you get a parts routing. Check that it's arrived with the previous operation having been done. That you are now the next one in line. Make sure you X the boxes. Okay, continue, please. That's your performance curve. So again, the goal is steepen this curve, shift the curve to the left. We can't avoid the warm-up period today. That'll be in the future. But the goal should be quickly complete all the jobs in the shortest amount of time. And quality and operating cost essentially become negatives. So the point is that if quality is good, you will essentially be delivering parts by due date. Okay? Next slide, please. This could be a performance curve. We'll see what happens next. Next slide. Okay, so we designed a process layout. Next slide, please. There was no one-piece flow allowed. That was your from-to chart. Next slide, please. Some more analysis. The goal was, again, people don't even design their process layouts well. They choose to be in a departmental mode of manufacturing. They don't even design their layouts with any forethought. And they use manual methods like relationship charts. On the other hand, if you're making, say, 500 different components, and 500 is small. Okay, if you go to a typical machine shop, a hospital, a forging company, sometimes they'll say we have 1,000 active numbers on file. Now imagine, people don't even work with 10 different routings when they design the layouts. Here with the from-to chart, you effectively have captured all the flows corresponding to different components. The problem is when you design a from-to chart, you are locked into designing what is called a process layout. So no matter what you do, if you design facility layouts to make different components which follow different routings with a from-to chart, you will essentially get a process layout. Perhaps the worst layout you could have for your factory. Like it or not, a process layout is the worst layout you could have. Okay? Great. Next slide, please. So, again, quick review. I ran my from-to chart in Storm. I designed a U-shape. The plan is that we'll have a central material handling aisle that forklifts and cranes will operate in. We have put all our departments on either side of the building. What's wrong with this facility layout? It's a terrible layout in my opinion. What was the good of using all this computer software if at the end of it you got this layout? But even this layout could be improved easily. You can easily put that into like an M shape. So the point again is that just because the computer spits out information doesn't help. Map it, discuss it. In some cases, companies create physical mock-ups, then go and implement the layout. Okay, what we did initially was we didn't even use this knowledge. We just randomly put you in. We allocated you into a process layout, and we had certain problems. Sachin, next. Okay, now here's the key. Machine number 4 was overloaded. So that's your first give. This people normally do not do. They keep cussing their MRP system. They don't have industrial engineers on staff. As a result of that, whatever work that they do, they never create these things called workload profiles. They all work with takt time and Hijunka because in assembly, capacity is balanced and you don't need these analyses. In high variety, high variable work, you need this load profile. So this is basically looking at all the components that go through 4 and counting all the squares over batch size. So see, 4 is heavily loaded, 7 is heavily loaded, 10 and 11 are slightly heavily loaded. Okay, so that's the first give to us. That one of the improvements could be looking at all the work going through machine 4 and doing some process improvement. So what we'll do here is we will look at the routings of these parts and just arbitrarily, again, this is a game, arbitrarily what we'll say is, you know what, we are going to improve the processing speeds, we will improve the equipment capabilities, the tooling, change the materials. With what goal? That the total time spent by all these jobs on machine 4, Stacy's machine, is say cut down by 50%. Okay? Right? Because again, keep in mind that machine breakdowns occur based on usage. Okay? And you can't have a flat preventive maintenance schedule where you don't look at usage rates. Okay? So that's the first give. Please keep that in mind, that we'll go through all the parts which use machine 4 and just say, you know what, process improvement Kaizen was conducted and we've essentially cut down the cycle times on machine 4. Why? Because that's a clear load, heavily loaded work center. Okay, next slide please.
But maybe,
yes, yes.
don't you want to look at customer demand in terms of establishing
Good point again.
attack time? Because maybe machine 4 is okay.
Yes.
And its current work content.
Yes.
If it's aligned with customer demand.
But the point is that you're spending so many units of time regardless of demand. You know, there's an unequal workload. So that means somebody operating machine 4 is saying, how come you're paying this machine operator 3 the same wages as me? I'm being utilized much more. And then there's a bottleneck issue. There's a work imbalance issue between the work being done on 4 and the machine sending it work and the machine it's sending work to.
Agree with the imbalance
Yes.
in cycle time.
Yes.
But if machine 4, for example,
Yes.
if that work content aligns with the customer demand,
Yes.
then that would be acceptable to have that, and then you would balance all the other machines.
Yeah, but my point is that why should I take, say, 30 minutes per piece? Could I take 20 minutes? I meet the demand. So 30 minutes per piece multiplied by a demand of 3 is 90 minutes of workload. I will still make 3, but now it will take me 60 minutes if I bring down the per piece time to 20 minutes.
Clearly that results in a lower cost.
Yes. Because keep in mind that if you don't reduce from 30 to 20, you've essentially got work piling up in front of 4.
Okay, we'll assume that that's just a bottleneck and we're looking at the constraint.
Yes, we're looking at the, yes.
But it's independent right now of customer demand.
Customer demand would be whatever parts are going through machine 4 are still being ordered in lots of 1, 2, or 3. Demand has not been adjusted. What we could look at is, what is the scrap factor you're assuming on machine 4? And if you are artificially hiking up the production quantity, suppose you have a 95% first time through, there's a 5% loss, you might come back and say, if I improve quality, I'm not going to be making the 5% number of parts extra. Okay, good question. Next step. So here's the goal, right? We ran that existing system. We ran the existing system, and there are the following ideas come up. If you look at the workload profile, Sachin, go back to that workload profile, please. The previous slides, just go back. Keep it. Yeah. See, look at this one here. See, that's the next thing we should look at. 3, 5, and 2. These are extremely underloaded work centers. So let's do this as an improvement. Let's fire a couple of machines. In a good kind of way. In a good kind of way. Yes. Let's see. I thought I had them here. Sure. Yeah, I know. That's what I'm looking for. Yeah. Let's see. Here we are. Okay, so let's do this. Let's do this. we want 2 of the operators across machines 3, 5, and 2. You are voluntarily retired. Okay, good. So Kramer's gone. Okay, we need 1 more volunteer to retire. The point again is that now you're going to and I'll show you why you co-locate 3, 5, and 2. I'll show you why there's a method to the madness. That 3, 5, and 2 essentially are going to be put together into what is called a module. It's not a cell. It's a partial cell. But you're going to put 3, 5, and 2 in like a triangular or U-shaped configuration and have 1 person essentially cross-trained to run these 3 machines. So you're retiring, very good, thank you. So I'll take this out. Just go sit over there. Take this out, okay? Yes, sir.
So with that, aren't you going to be like going back and forth with sanitation a lot?
Sure, but then essentially they'll be busy. 1 person will be a little more busy. They'll be splitting their time. It's basically labor constraints. You've got 3 machines, 2 of them will be idle or in cycle, while this person is maybe setting up the 3rd machine. Okay? Go ahead now. Okay, come back. We'll discuss that again. Okay, so here, Carl, we will take away all of these machines from you. I'll put you in charge of 3, 5, and 2. Okay, so just remember your. Okay, so that's the first. Yes. Yes.
To do that, you have to physically relocate machines 3, 5, and 2.
Good point.
Area where the operator will be traveling.
Very good point.
Traveling from machine.
Correct. So that's the idea. The idea again is that because the routings, and I'll show you how it comes about, because the routings indicate that there are several parts which are going through 3, then 5, then 2, or 3 and then 2, you're just locally having cellular manufacturing. Just locally you're saying, you know what, in the best case, let's put these 3 machines together, let's cross-train the employee so that products will flow more efficiently between the 3 machines. Exactly, and you will see that. We'll see that, yeah. You'll see that, exactly, okay. So that's one other improvement. So here's the thing. Let's look at the routings of all the parts which go through 4 and just make some decision. At this point, just keep it simple. Let's cut down half the squares that all those parts require machine 4 to X out, okay. Another improvement that you look at is, since the loads are low, and also the fast analysis of the routings will indicate something, that there are at least a few products which go through these 3 work centers in a certain patterned manner. Okay, so by putting Carl in charge of the 3 machines, what you're doing is quickly gaining the benefits of cellular manufacturing. See, typically what people do is, oh, let's go to cells. And they go and implement these multiple cells. Oh, these are mini factories, etc., etc. But cells have a problem. If the demand is variable, and the mix is variable, cells are a colossal disaster. So instead of cells, one concept is what they call partial cells, or what we call modules. 2 to 3 machine pockets, internally there's efficiency. It's not as good as a cell, but it's a lot flexible. You don't have to worry about co-locating too many pieces of equipment. The other benefit I've found is that by creating modules, you have a logical basis to go to flexible automation. It gives you guidelines that if I buy flexible automation, what capabilities should this new equipment combine on one work center? So there are some benefits to be gained there. Okay. Next slide, please. Just keep going further. Round 2, yeah. Okay, so now, then the next question is, one-piece flow is good. You know that one-piece flow is good. How does one-piece flow normally happen? Do you keep a process layout and then have one-piece flow? No. There is no way that one-piece flow will happen if you don't physically design layouts, preferably cells or lines, where consecutive work centers are within easy reach of each other. Okay, and we know this policy works. We know that this policy works, okay? So our goal would be, ideally, to create manufacturing cells, okay? So that's the third thing. Combine, cross-train people to operate combinations of lightly loaded work centers, cut down the work content of parts which go on machine 4. So Stacy, please do this. Look at all these parts, Look at all these parts, and wherever you see 4, just cut out half of the number of squares. Okay, so for example, this one, just X them out, just draw a line through them to indicate, or use the purple marker you've got. Just
Can I
for example,
round up?
Sure. Yeah, sure. Absolutely do that, okay? So the point is that, one, the water strider becomes more of an outside operator. Two, jobs get progressed by the operators themselves. They take charge of delivery, okay? Then you look at design for manufacture. This is what we mentioned about machine 4. That we go back and say, those work centers are being heavily run. Can we do something to cut down the cycle time on those parts which go through 4? So Stacy, be careful, just as I said, count the number of squares, divide by 2 and use the purple highlighter. Eliminate those operations, okay? Next step, please. Next slide. Okay. Then, could we use some logic for work order release? Now, look at your routings. Look at your routings. Can you look at the total revenue that in your handout on page 3? Can you look at these different part numbers and say, you know what, from a cash flow perspective, certain jobs earn me a lot of money and certain jobs don't? I mean, why do you want to be in business making unprofitable jobs with too many steps? Why? Right? You're in the business of making money. August, yes.
Well, isn't there cases where like it's a popular product or something and you need to keep it customers happy?
Sure. Sure, then again, I'm looking at the total sales value. If it's a popular product, it's a high volume, and the sales value is high, I retain the product.
Well, not like popular product, just
Yes.
something your customers want, that your like regular customers want. Something that you cut out, you probably lose customers. Even if the popularity isn't that high.
Right, but then the point would be that if it's a high volume, low per piece priced item, you probably want to run that in a separate line balancing, assembly line kind of shop. Good point. My point is that if you're doing a high variety of work, quantities aren't high, cash flow varies across the work, from a business perspective, you want to spend per hour of labor earning the highest dollar rate. So like Goldratt's objective is, what work am I doing that is earning me the highest dollar per labor hour? Okay, so in this context, what we are doing is something called mix segmentation. Look at your work mix, and from a value perspective, I'm saying sales perspective, for my release work, I'm going to start work off that potentially earns me more money for the work I do, and then later on I bleed in the less sales value work, okay? So you can choose other parameters. My point again is that let's have a priority that when we run work first, we run work which we think is more important, and then when we run work later, let that be work which we think is less important, okay? So my point again is that there are different criteria, and it becomes harder as you start using more data. It's easy for me to say rate of earning, but you know what? Imagine the shop floor. They don't even know the work content. They're kind of winging it. Secondly, management has not given them any value measure of the work that they're doing. So for the operator to make a decision line side or machine side on something like this measure is bunk. My point again is that, look, either the operators can do it, which is best, or management and production control and foremen are able to do that. If nobody is responsible for that, you end up running a business where cash flow gets sacrificed. So somewhere or the other, you decide mentally, look at the data I've given you on page 3, look at the last column. Total value of that batch, of each order. There are values like $1,200 on certain jobs, there's another value like $825, and then there are other values which are very low. So in some cases, if cash flow is the objective, you want to start the shop, the cells doing most valuable work first and then less valuable work, okay? So look at the mix of jobs. Tell me from a source. Yes, yes.
But one of the things they never do on routings is
Yes.
say the value to the
Absolutely, absolutely, and I admit that.
It's not apparent to them. If they have two routings and they're equal because they're printed on the same piece of paper.
Absolutely, but I guess what you could do then is at the production control level where you're scheduling the jobs, over there the ERP system feeds in some information, the scheduler, which says between these two jobs, this one has the higher dollars earned per labor hour. So to your point, there are some constraints about giving too much information to the shop floor, but then there's a downside to that then your shop is kind of winging it. And what is typically done? SPT, shortest processing time. The operator basically looks at the work they have in front of them and says, which one can I do first? Damn the due date. I did a high setup, let me run a job which has the same setup. I picked a job 3 weeks into the future and I sacrificed 2 jobs due tomorrow. Who cares? I'm going to do my job best, right? So that's another strategy. Get in, like some people, what they do is they don't give the dollar value. I've seen cases where they use color paper. The travelers, the job packet, red indicates high priority job, always. Green might indicate low priority work. Okay? Yellow might indicate prototype, something like that. People look at the paperwork that's shoved into the part number in the container and they say, okay, this means I should do this work first. So somewhere or the other, decide for yourselves, is there any priority that you would associate with these 17 jobs you have? So look at page 3, the last column, and then tell me, should there be some priority assigned as to which job gets worked then? So that's another thing. It's called mixed segmentation. Go back to the second or third week of this course. Remember we did things like PQ analysis, PQS analysis, PQT. Q and T is demand stability, volume as a function of time. PQS is Q is volume, dollars is value. So volume versus value. If you have low value work being done in high volume, it's a consumer product. You'll probably lose it to Vietnam or Asia or someplace else, okay? This country, at least if you read the Time magazine, last week's issue, or last month's issue, this country is going to remain in manufacturing doing high-end, precision, high-skilled work, period. That's it. All the white goods, que sera, sera. At least that's what I've heard, okay? Then, could you sequence the jobs? Now again, I think it's very difficult to compute all these parameters to take these decisions in real time. But you know what? If you don't do it at all, what you have is a badly operating factory or a badly operating hospital or a badly operating office, period. So the point is when you do layout design, you keep looking at all the other support systems. Methods analysis, production planning, scheduling, ergonomics, you look at them. You cannot ignore some of these issues because something like this will impact the floor space you allocate in front of a machine. Some of this will impact the signs you put in front of the machine. For example, you have a hang tag, right? You might have a small card associated with that container. That card, you'll pick it up and you want to clip it on that hang tag because then the operator says, okay, I will pick the card off the top of the list. They call that Kanban board or schedule board, whatever. But the point is that this information like this is going to drive layout-like information. All the 5S which you do, the workspace design that you do, the Kanban squares which you draw, all of that gets influenced by these decisions. So I would say mentally think about whatever machine you are, look at the value of the jobs, and mentally decide that if there's a queue in front of you, which job will you run first? Okay? Next slide, please. Okay, so the next step then is, we know that cells work. So the classical change of a layout, an existing layout, to a better layout, we will assume away the fact that the mix and the volumes could change, okay? But it is proven that cells are a good way to run a factory, especially a factory that's non-assembly. So we're going to design 2 cells. Here's what's going to happen. Some equipment will need to be duplicated. We need to know which ones. Do we have the money to buy them? Are they monuments? Are they cheap machines? Are they easy to operate? Those issues will kick in. Because when you create cells, same capability may be necessary over 2 or more cells. And that is not a trivial problem. You might say this, well, I will put this equipment in cell 1. And after cell 1 is done with their work, I will let cell 2 bring their work to use this machine. Guess what? You destroy the delivery of those parts that cell 2 is making. Okay? We will also look at this issue. You really need to duplicate equipment? Could we change the layout in such a way, especially look at machine 1? And you'll see why. If you do a detailed analysis of the routings, you do not need to buy an extra machine of 1. Okay? Now, we will give each cell a U-shape. You've already been through a quiz or quizzes that have said, well, that's not the best way to shape a cell. We'll assume that that's okay. Next slide, please. Okay, then here's key. We will allow one-piece flow inside the cell. Now here's where I would like the machines to be a little cooperative. Okay? Thank you. So let's take this case here. Part number 1 has a lot size of 2. Okay? It's got a paper clip. Now, if your machine 1 is starting off, where's machine 1? Yeah. So your machine 1, right? Please don't throw away the paper clip. Okay, so do the first part. When you finish the first part, put the paper clip on that piece and then just pass that sheet on to machine 4. Then you start on this one. Okay, that way you're splitting the batch, but then I keep the container with me. Okay, so when both the parts are completed, I will containerize them. My Kanban square will be complete. I'll pick it up and I'll consider that a shipment. Okay, so please, the machines, if you get a batch of 2 or 3, be diligent. The moment you finish off the first piece in the batch, kindly put the paper clip on that first piece. And then, if you want, pass it on to the next machine. Please don't lose the paper clip. It's like losing your container. Okay, you can't have that. Okay, and then you can continue processing the second and the third piece of that batch. Okay, so this is a simple way. This is a simple way of doing one-piece flow, even in a job shop like cell. Inside the cell, you have containers like push carts, small capacity mobile containers. You can move smaller batches inside the cell. It doesn't have to be a very large area, but outside the cell, you are using the containers that are used for shipment and big batch handling. You understand that? That again, layout design. We did the material handling analysis chart that had to do with containers, batch sizes, handling equipment, etc., etc. We are simulating this natural thing to do. In lean, when you are working in a small space, a cell, and you're trying to have one-piece flow, you use either the piece itself as the container, okay, or you essentially have very small, like totes or tabletops or little roller racks. The goal is inside the cell, you're not moving the demand quantity. The demand may be for 100 pieces, but inside the cell, you're moving lots of 5. So the container holding 100 pieces is still outside the cell. When that container is completed with 100 pieces, that 100-piece batch gets shipped. But inside the cell, you don't destroy ergonomics and floor space and labor motion control by releasing those big containers into the cell. There, you pick 5 pieces, machine them, move them on. So, okay, so that's my request to all the machines, that inside the cell, you'll do one-piece flow. Please don't lose the paper clip. Okay. Okay, what else? So inside the cells, machine operators can deploy one-piece flow and hand over parts. I, the water strider, will ask you to give me some directive. You as a group are going to tell me in what order I should release the work into the cells. Here's how we will do that. You will tell me, you will place one beneath the other. You will put certain parts which will be going to cell 1 and cell 2. I will release the first part from the stack. Once the operator pulls that, I will bleed a second part. That's Kanban. Consume 1, give 1. Consume 1, give 1. Why? I don't want the cell area to be just full of pallets and containers and tubs. I don't want that to happen. Okay, so I will expect from you some advice about in what order do I put these jobs in front of the cells. Okay, I'll ask you for advice. Next slide, please. Shipping must be done as a batch, and therefore I'm going to be collating. So as a water strider now, I trust you inside the cell to do your business. No material handling is going to be requiring a forklift guy with a crane or whatever. None of that will be necessary. Only thing necessary will be the handling will be to support the logistics outside the cell. Stores coming to the cells, from the cells, going to shipping. That's how it will work, okay? So, what's our next challenge? Next slide, please. How do you design the cells? This is where basically we start using our good old software tools, okay? So, let's do this. Here we go, yeah. Okay, so remember we had those 16, 17 routings on page 3? What is our goal? Our goal is, hey, how do I physically change the layout in such a way that now, instead of a process layout, I go to a cell layout, correct? So I take my data, go ahead. I've read the data, I run the analysis. That's it. So the goal is that I want to be able to design a couple of cells. So that was my input data. This is where I start. This is my good old product process matrix, correct? So looking at this information, what would you suggest would be potential families of parts? Remember we said, what's a family of parts? It's a bunch of part numbers that pretty much use the same equipment. So the equipment is listed across the top, your part numbers are listed down the bottom. Each of these ones captures the fact that this product or this value stream requires this asset. So how do you look at something like this and say, well, I can design 2 cells? Some of you may have gone through this for your projects, some of you may not have. I mean, this is basically where the rubber hits the road. In reality, this is where we begin with any complicated problem. So what do you make? Are these things different because they go through different equipment? Good. Give us your routings. So if you look at this output, what do you do with it? Yes, sir.
There almost appears to be 2 groups like.
Good. Please, would you come up, please? Please, please, yes. Again, give me your ideas. Give me your ideas and we'll discuss why you chose what you chose.
Right here there seems to be a group.
Good.
Right here seems to be another group.
Good, thank you. So now, if I were to challenge you and say, please draw a line across, that is, if I were to say, please draw a line somewhere here and say, you know what, above this line is going to be stuff in one cell, below this line is going to be stuff in a second cell, give me a line. Don't worry about right or wrong. I'll argue with you, I'll discuss with you. I'm not trying to show you up, but give me a suggestion. See, we talk about Kaizen and Kaikaku. We use all these words we don't understand, right? The point again is that the right analysis given to people who are then challenged, now tell us how the factory should be, is a good starting point. With the software tools, we give them a decent starting point. Not perfect, but a good starting point. Yes, sir. Go ahead.
I mean, probably do it like
Okay.
right about here. Like,
No, horizontal line. See, what I'm saying is, see, these are part numbers, right? So what you're saying is if I draw one line, above this line will be one part family, one cell. Beneath this line will be the remaining products in the other cell.
well,
Good.
here's down.
Good. Okay.
Up.
Good. So here's the point. This is Greg's idea. This is my idea. Now, Greg, if he had more time, if he had number crunching capability, a simple spreadsheet, some ERP staff people being able to run the workload numbers, he might have come back and said, beneath this line is one cell, above this line is the other cell. Now, let's look at the equipment sharing. Let us look at the equipment sharing that's involved. If I say that products above this line will be produced in one cell, and products beneath this line, let's look at this line here. Above this line, okay, machine 2 is unique to cell 1. No problem. Machine 3, above this line, Below this line, nothing. Automatically, machine 3 is unique to one cell. No problem. Next machine, machine 5. Above this line, parts 8 and 9 needed. Beneath this line, no parts needed. Wonderful. Machines 3, 5, and 2 are unique. Brian, could you go back to results and show me the routings output? Results. Yeah, show me the product routings. Product routings. Next, yeah. Look at 3, 5, and 2. Part number 9 goes 3, 5, 6. So you see 3 is used and then 5 immediately, okay? Part number 8 is 3, 5, 2. Again, when machines 3, 5, and 2 are used, they are used 3, then 5, then 2, okay? Then this goes up further here, 1, 2, 1, 2. So what you can see over here is that there are at least 2 part numbers which are consecutively using 3, 5, and 2. And therefore, there was the basis of saying that, you know what, let's put these 3 machines in a pocket and have one person use them. Brian, go back to the PR1. Next, yeah, PR1. Okay, so at this point, now you see a problem. Machine 6. If we had to create independent cells, we would have to put one machine 6 in cell 1 and another machine 6 in cell 2. So 6 becomes a sharing problem, potentially. How expensive is it? Is it a monument? There are issues like that to be considered. So if you had machine 6 as a monument, forget it. It anyway cannot be put inside the cells. Anyway, it's a problem, right? But 6 might be what is called a grinding machine. Very expensive machine. Very expensive machine. Management is not going to be happy if you say, let's buy 2 surface grinders. And guess what? In each cell, they'll be used like maybe 50% of the time. You have no ROI to offer. If you say expensive equipment, which should be used half of its time, you're going to put 2 of them, and which means buying 1 of them extra. So there's that challenge which kicks in. If you designed 2 cells at this point, one cell producing parts 8, 9, 7, 10, 2, 1, 3, 4, and the other cell producing parts 6, 5, 18, 14, 15, 12, 17, 13, machine 6 has to be analyzed. Then look at the next machine, machine 9. Once again, if you broke the part family here, one cell will require machine 9, another cell will require machine 9. Okay? Go across further. Look at machine 8. Only one part in this cell will use machine 8. Most of the machine 8 utilization will be in this cell. So that might indicate to you, maybe the part family should have been modified. Maybe. Continue further. Machine 4, you see it's unique to cell 1. So that's good. Machine 1, problem. There is 2 parts using machine 1 in this group, and there is 4 parts using machine 1 in the other group. Now, looking at this output, wouldn't you naturally say, well, I need to put a machine 1 in cell 1 and a machine 1 in cell 2? Wouldn't that be the natural conclusion? But now let's look at the routings. Could you go back to routings, please? Look at the way machine 1 is used. It's basically a primary machine. It's like the band saws. Okay? All bar stock has to come and get sawed, right? So if you look at these routings, part 1 uses machine 1 first. That's it. Come down further. Part 15, part 2, part 3, part 4, part 5. All of these products, their routings use machine 1 as the lead-off machine, which means that you could easily have 1 as a shared resource and then build the 2 cells around the shared resource. And I'll show you how that looks essentially, okay? Go back to the PR1, yeah. Okay. So, to my point, what I'm saying is that, okay, I've spent some time on the analysis. My recommendation would be to break the matrix here, okay? Okay, so that means you're breaking the matrix in such a way that machine 1 is shared, machine 7 is shared, and machine 10 is shared. Just go back to the PowerPoint slide, please. The PowerPoint slide here. Slideshow. slideshow. Okay, so go back to the next slide, please. That's just some outputs telling you what the part families look like. Next slide, please. Here's the point that now when you break up your part families, see, machine 1 is hardly used. So the point again is that in the layout, it is not necessary for you to separate this equipment. Put that in a common location, and depending on the schedule, that machine 1 could be used to make parts in cell 2 or cell 1. Okay? Secondly, machine 7 and machine 2 have a reasonable load. So what you can say here is that from an equipment purchase point of view, I may have to invest in an extra copy of machine 7 and an extra copy of machine 10. So at this point, I want a couple of volunteers. I need a couple of volunteers to pick up machines, and you just seat yourselves wherever you have an extra chair. You will become, this is called duplicate machine 7 and duplicate machine 10. Okay, so duplicate machine 7 and duplicate machine 10. Thanks, Kramer. Welcome back. You've been cross-trained and now you're a new employee. Okay, good. Please come, please.
Come back.
Good. So the point again is that if you have to invest in equipment to make the cells independent, this output, this workload analysis is giving you a sense, you know what, look at the utilization. Depending on the utilization, be careful about buying extra equipment. Okay, so even though I have cells, I'm not being very dogmatic that, oh, they have to be independent. If the utilization is poor, I go with a common resource. And because machine 1 is a lead-off, kick-off machine, I know that I can build the cells around this common resource. Okay? But I've decided to invest in these two pieces of equipment to make my cells independent. Now, the question is, what do you do next, please? So, you take your two-part families, again, you've been through this, right? You take the two-part families, you create separate input files for FAST, you compute the from-to chart for each part family, put that into Storm, design the U shape, right? So any questions please about that? I took all my parts, I tested where to create my part families, I did some load balancing analysis, and I said, you know what, this is what needs to be done to make these part families good. Once I had a sense of what equipment to put in the two part families, I separated the data, created two separate files in FAST, ran some numbers, got the from-to chart. With what purpose? I'm going to put the from-to chart into Storm, and once again use Storm, this time to design U-shaped cells for the two-part family. So next slide, please. Output analysis, blah, blah. Please. From-to chart for the next part family. Next slide, please. This basically becomes the starting point. Okay, so I took the from-to charts for the two-part families, exactly as they are, put them into Storm. So here's my challenge to you. You know whether you're cell 1 or cell 2, correct? How? Let's take the existing machine 1. Let's take the existing machine 1. Go to the next slide, please, Brian. I flipped one cell around. I flipped the U around so that now my machine 1 is a kickoff machine. I bring in raw material. I have painted racks. One paint represents cell 2 raw material. One set of painted racks represents cell 1 raw materials. It's very visual, but the asset is not having to be physically duplicated because one of those saws would be underutilized. So what I've done here is I've cut out the need to go and unnecessarily buy equipment. Now somebody might say, you know what, I have seen this company go out of business and we can buy one more of machine 1 cheap. Those kind of decisions to make the cells independent, way to go. I'm just giving you examples of all the solutions possible to streamline layout designs, keep them lean, yet flexible. Okay, so here, this is flexible. Because depending on the mix, the capacity on this machine 1 could be put to make cell 2 parts or cell 1 parts. But physically, they have access to the appropriate raw material racks. They can pull on demand from the schedule which cells parts they need to work, okay? So please do this. You already know if you're a duplicate machine 7 or a duplicate machine 10. So if you're a duplicate machine 7 or a duplicate machine 10, you go to cell 2. You bond with the other machines in cell 2. So who's machine 1? Good. Let's do this. You will please sit here. Come here. See, imagine this way. You are machine 1 like this, okay? And then cell 2 will be on my right, and cell 2 will be on my left. Oh wait, I'm sorry, Kendra, I don't listen to it. Yeah, please come. Here, come here. So you're machine 7. I apologize again. This is cell 2. I'm going to pull you. Sorry. Sit down, please. Okay. This is machine 1. Cell 2 machines organize yourselves into a cell in a U this way, and cell 1 machines organize yourselves in a U this way. Okay, so imagine this way. This is Kendra here. She's sitting here. Cell 1 is going to form as a U in this order, and you please adjust the shape of your cell. Just because the computer output came this way doesn't mean implement it. The point is that it's a very good start. Okay? Cell 1 machines will organize themselves this way. So let's see. Who's the duplicate machine 7? Kramer, please come here. Now bring your chair up here. Thank you. Come, sit here. You sit this way. Okay? Duplicate machine, the machine 11 is not duplicate. Machine 11, please. David, come here. Put yourselves across here. This is the beauty of cell manufacturing. Close proximity, communication, feedback, teamwork, clear performance measures, clear control of how much work is sent in, small areas between the machines to prevent push of work. Keep all the work outside, bring in only how much you can work on, and move quickly inside the work area, okay? Duplicate machine 10, please come here. Amy, come here. Daniel, you please go to that side. What about your you want to use, okay, come on. Yeah, you got, yeah, sure. Come here, machine 10, yep, and machine 12. Eric, please go to that side. Good. Now, this is done. Let's look at machine 1 organizing themselves. Cell 1, that's, yeah, Kramer, you might want to just move a little bit more, just away from, oh, Kendra, just come this way, a little more. Yeah, little more. There you go. Good. Okay. That's machine 1. Then machine 3 will serve. Where's the 352 work center? Carl, you please come here. Kendra, I think you might want to leave a little more. I think just, yeah, good. So that's the module. Okay, so look at all the things which we're doing. We decided to go with a common resource because we felt it didn't make sense to buy an extra copy of machine 1. Okay? We decided to group locally underloaded equipment into one area and cross-train a person to run 3 machines. Okay, so that's Carl. Okay, then there's machine 6, there's machine 4. Machine 4 engaged with a continuous improvement team, and what she has done is she's basically said, you know what, I've cut down the cycle times, the workload to some extent to reflect the fact you don't want a big spike in the work that she does. Okay, okay, then that's 6, then machine 4, good. Then machine 7, there's machine 10, machine 10. Who's a machine 10? Please come here. Let's put this away. Yeah, oh sure, come here. Let's see. Machine 10. Put your label here, machine 10. Okay. Then machine 8. Good. Eric, go a little closer. Machine 9. August, come here. Let's give you a chair here. Can you give me some advice about what jobs to put first? See, here's the thing. My question is this. See, hear me out, please. Here. I'm going to sort through all the jobs. Let's see, which jobs go through cell 2? Can we go back, please, Brian? Which jobs go through cell 2? Okay, so let's see. Jobs 14, 15, 12, 17, and so let's see. 17, then 15, then where's 14? 14, 12, 12 and okay, so here's cell 2. Here's cell 2. It goes through 5 parts. Okay, cell 2 goes through 5 parts. Parts 12, 13, 14, 15 and 17. Now, part number 12 goes through machine 11. Part number 13 goes through machine 11, already a queue. Part number 14 goes through machine 11, already a queue. Now, part number 15 goes through machine 1. So what's the decision? Should we basically have part number 15 done first by Candra, the shared machine? I'll leave it to you. Okay, that's the first question. It's a scheduling question. So there are 4 parts which go through machine 11. I asked the group, tell me in what order to put them one above the other. What goes first? What goes next? What goes next? Any advice?
You don't have any visibility to customer due date, do you?
No, it's purely at this point I have to make, yeah, good question. The question asked was, do you have any due dates? I don't. It's pretty much make these parts and ship them as quickly as possible. So, yes.
Do you choose what makes the most money first?
My bias, but if you feel something else should be done, I will respect what you say. So, which one do I release first? Okay, good. So let's do this. I'm going to put 15. So Candra, just hold on to this. Okay, let's see what's most easiest for you to reach. I'll leave it here. Okay. So I'll leave part number 15 in queue. Okay. Now I've got part numbers 12, 13, 14, and 17. They're all going on machine 11. So this machine operator is going to come to my supermarket, my active parts order supermarket, and pull the parts one by one into queue. So which one do you recommend first? Does 12 go first? Does 13 go first? 14 or 17? Tell me. Good. Next. After 13? Okay. 17. Good. Then 14 and then 12. So good. So David, you are the machine operator. So in the interest of simplicity, you come up, pop this stack, pick the top part, okay, work it on your machine and then pass it on. Okay, then you come forward, pop the next element. So just to see what you're doing effectively here is you are doing what is called pull scheduling based on realistic workload. Why should I jam this work area with 4 big tubs, multiple containers, when really you know that he's going to start first and pull something? Okay, so that's the queue of work in front of him. Let me just cascade these. Good. Now, machine 1 is the bigger issue here. So, decision time. Here's the deal. Management or the cell foreman have to be cooperative. You know that machine 1 is really only using one part or only processing one part in this cell. If this cell selfishly says, go to hell, forgive my use of, it's not a swear word, but it's a swear word. From a business point of view, what you're essentially saying is, let's not disadvantage cell 2. So the first setup that this shared resource will go through would be a part for cell 2. Even though much of her work is coming from parts produced in this cell. This is classic scheduling measurement. If you'll go through any scheduling in other courses, the point is that if you do all the parts on machine 1 for this cell, this person is going to be waiting till the end. And that cell could not get the work done. So it's called shortest processing time. You're basically saying, if I were to use machine 1, let me quickly get work done on cell 2, because really cell 2 doesn't deserve to have to wait for its part. There's only one part using it. Then, after that, the setup for cell 1, machine 1 will be completely dedicated to only the work which cell 1 is performing. So, I'm going to put part 15 on the top of the stack. Okay? Now, let's look at how I will deliver parts and sequence parts to the supermarket for cell 1. I have part number 1 goes on machine 1. Part number 2 goes on machine 2. Part number 3, 1. Part number 4 goes on machine 1. Part number 5 goes on machine 1. Now, Part number 6 goes on machine 6. So now what I do is I create lanes. I create dispatching lanes. Physically, I will sequence the jobs on machine 1 in this lane. Okay? Now, let's look at part number 6. It goes through machine 6, separate lane. Part number 7 goes through machine 6, same lane. Part number 10 goes through machine 4. So now I have to create a supermarket lane for machine 6. You're putting down flags. And what you're saying is, work for machine 1, work for machine 6. There's the same idea, they use that a lot at a Honda or a Toyota, where in shipping they put little labels on the walls, and pretty much what they're saying is, this is part number this shipped to such and such person. This is part number this shipped to such and such person. Same principle, just exploiting scheduling, you're applying it in a high mix job shop cell. Okay, part number 9 goes on machine 3, part number 10 goes on machine 4, part number 18 goes on machine 6. So that's here. So question to you. There's a part which goes on machine 3, and there's a part which goes on machine 4. Not much choice here. So machine 4, you will have to come up here and pick up your work, okay? Machine 3, you will have to come here and pick up your work. So the rest of you, tell me, as far as the work going on machine 6, I've got 3 parts, 6, 7, 18. Which goes first, which goes last? If machine 6 walks up and picks up one job, which one should they work on first, next, and last? So I've got 3 parts, part 6, 7, and 18. Good, so 18 goes first, good, then 7, good, and then 6, okay? So I'm going to sequence your queue as follows. I'm going to put 18 here, then 7 here, and then 6, wait, there's a mistake. 3, wait, I think I screwed up here. Part number 6 goes to machine 6. Ah, I knew there was another part missing. Yeah, sorry. Here's the thing. I think I know what's going on. Okay, there are 2 parts going on machine 3. Part 8 and part 9. Which one goes first, which one goes next? 9. Good. So part 9 goes first, and then part 8 goes next. So Carl, you'll be picking up part 9 first, process it, and then pass it on. Come back and put up the next part, okay? Then, over here, I've got part 15 goes on machine 1, part 1 goes on machine 1, part 2 goes on machine 1, part 4 goes on machine 1, and part 5 goes on machine 1. How do I sequence these jobs? 15, 1, 15 goes first, so there's no problem. Between 1, 2, 4, and 5. How do I sequence them? Okay, so this is 15, then I put 5 here, good. Next, 2, okay, 2. What about 3, 4, and 1? So right now I've got 15 goes first, then 5 goes next, then 2 goes next. What about 1, 3, and 4? Good, 3, then 4, then 1. Ideally, I would have had a electronic signal, some light, something which basically would say, part of what the first order has been pulled by this machine, bring me the work for the next job. Okay, so each machine's trigger, there might be a barcode wand or a light or a walkie-talkie. The point is, don't jam everything in to a small workspace. Defer the inventory at the cheapest point, raw material, okay? Okay, so against that background, very quickly again please, if you see a batch of 2 or 3, kindly put the paper clip on the first piece, process it, move it on, and then continue with the rest. Inside the cell, you are responsible for moving work to the various machines. You are most responsible absolutely for quality. Okay? Are we ready? Yes, please.
So
Yeah.
the ones that are crossed out, am I just not doing them?
You won't do them. You won't even X. Exactly. So the nice thing is you have that purple marker. So basically, you don't even have to X those areas. See, you can party. That's yeah.
So you just cut out all that work?
Yeah. So the point was, I felt that 4 was overloading with work, and so what we did was we said, put a little more balance, tamp down the workload on machine 4, do some process raising, which a lot of people would do.
So where did that work go?
It was basically cut out. The cutting time has been cut down, the tool insert has been used, etc., etc. Yes, it's a form of local process improvement. See, workload comes about through at least 3 factors: changeover time, cycle time, and the quantity you produce. So SMED attacks changeover time, process planning attacks cycle time, and production planning, scrap production, etc., hygiene cut, etc., attacks the lot size. Okay. In this case, we don't have a lot size issue. 1, 2, 3, big deal. We don't have setup time, so really cycle time. So the point was that machine 4 basically, the condition monitoring system said too much work content. This has got accelerated failure. So cut down the workload. So this is one of the things that people would do. It's called over-processing waste. 7 types of waste, over-processing. This is where some machines are running too much and some machines are running less.
I was just curious
No.
as to how we cut the work out.
Magic at this point, but in practice you will get the tool engineers on board, you will get the material buyers on board, the machine operators and the machine vendors on board, and get them into a cross-functional team.
I'm good with magic.
That's right. Yeah. Okay, good. Are we sure? Is Cell 2 sure about what they're doing, Kendra? We have had a production meeting, and you're going to do their part first, and then on. Okay, ready? Are we ready, guys?
No,
Yes, David.
For my part, I'm not waiting for her, and I'm going to get it right away.
Yeah, absolutely. Yeah. See, what she will do is once she is done, she will basically come and pop the parts at the top of the queue there. Okay, Kendra. So when you see, here's the thing. You will get this one, correct? You'll process the first part, put the paper clip on that, and go walk it over to that location. Yeah. Okay. So for whatever it's worth, are we ready to go? Okay. Are we ready to go? Go.
When I'm done,
You give it to me. Yeah. When you're done, every cell just drop your parts off in the appropriate queue in front here. Okay. I'm the water strider. I'll take charge of collating things, batching them, and shipping them. Okay. Yeah, just put it here. Yeah, just put it here. Good. Yeah, put it here.
Now, this is all stuff that starts on 11.
Yeah, you can get it when it's. I don't know if it's on.
It's all machine 11.
I'm busy right now.
Actually, we want you